given a graph, right, and a pair of vertices u and v, we write, let's say u is u is reachable from v, right, and v is reachable from u, or u is u and v are interconnected, right? If there is a path connecting u and v, right? So if I can go from u to v as well as from v to u, then I will say uv is an interconnection relation. Now this interconnection relation, right, uv interconnection relation is an equivalence relation. I want you to prove this an equivalence relation, showing that it has all the three properties. And then the equivalence classes under the equivalence relations are called the connected components of it, right? So for a graph or a diagram, right, the interconnection relation basically partitions into connected components. So components are, so for example, in the previous example, you will see that 1, 2 here is a component, right? 3, 4, 5 is another component. Then 6, 7, 8, 9, 10, 11 is another component, right? So these are the examples in the case of graphs. And yeah, so the equivalence classes under this relation is called connected component. Now this tells us, yeah, here is another example, right? You have C1 is a component, C2 is another component, C3 is a component, and C4 is a component. Now it follows that the components are actually maximal connected subgraphs by the definition, right? Because it is the equivalent classes under the equivalence relation of reachability, right? So u and v are reachable or interconnected. Then you are looking at the equivalence class, which means that it's a maximal connected subgraph. What I wanted to emphasize is that one, two, three here is, for example, a connected subgraph, but it is not a component because it is not maximal. Because 4 is also reachable from any of these, and similarly, any of these are reachable from 4. Right? So therefore, all these 4 vertices from a component, where any subset of that is not a component. Similarly, C1 is a component by itself, C2 is a component by itself, C4 is a component by itself. Now, D can be a digraph, and then again the interconnection relation u to v, if and only there is a uv path and a vu path, right? Then the interconnection relation is an equivalent relation, and again the equivalent classes are called strongly connected components. Right? So the strongly connected components are the equivalent class under the relation for the directed graphs, and for the other, it is the now. So if you look at this, can you find out the strongly connected components? So think about this for a minute before you look at the solution, right? So it's fairly easy. You can verify that this part, including the vertices 4, 5, 6, 10, and 11, forms a strongly connected component, because you can go from any vertex to any vertex. For example, 10 to 5, I can go through 11. 10 to 4, I can go from going to 5 and then going to 4. Similarly to 6, I can go through 4 and then to 6. Similarly, 6 to 4, I can go, 6 to 5, I can go, and since I can go from 5 to any other vertex, this also allows us to make sure that this is a strongly connected component. Now, that is because I cannot, for example, I cannot go from 8 to 6, so therefore this part will not be there. Now, so this is one component. Then you have another component, 7, 8, and 9. One can see that it's a directed cycle, and there's a reachability between any two. Then 1 by itself is a component, because I cannot reach anywhere from 1. And then 2 by itself is a component, 3 by itself is a component. Right? By 2 itself, because 2 to 3 I can go, but I cannot go back from 3 to 2. And 3 again is itself a component, I cannot go anywhere from 3. So we have this strongly connected components. So that we have 1, 2, 3, 4, 5 of them. Now, a nice homework is to show the following: that if C1 and C2 are two strongly connected components, then if there are edges between the vertices of C1 and C2, then they must all be in the same direction. Either all the edges are oriented from C1 to C2, that its starting point is in C1 and ending point in C2, or all the edges are starting at vertices in C2 and ends in the vertices of the component C1. Now a couple of more definitions. So if A and B are subsets of the vertex set V, X is a subset of, let's say, the vertex set union edge set. So X is some vertices and edges. Now if A, B and X have this property that every AB path in the graph G contains a vertex or edge from the set X, right? So then if I remove, right, X, then A and B are basically disconnected, right? So basically we can call X to be a separating set. So X separates A and B if X is a subset of B union E, such that every AB path in G contains a vertex or edge from X. Now, if I'm just looking at subset of vertices alone, right? X is subset of V is separating, then X is called a vertex cut, right? So a separating vertex set is called a vertex cut. Similarly, a separating edge set, right? If X is subset of E alone, right? There are no vertices in X, but just edges. Then it is an edge cut, right? Remove the edges of X, I can destroy the connection between A and B. It's basically an edge cut, AB edge cut, and similarly AB vertex cut. Now a cut edge or a cut vertex in a graph is either an edge or a vertex whose removal increases the number of components of G. Okay, right? And or one can modify it slightly by saying that either it increases the number of components or it gives you the trivial vertex. In some cases that could be useful, but for the time being, we will just we will assume this. So a cut edge or a cut vertex is basically an edge or a vertex whose removal increases the number of components of G. Now here are some examples, right? So if I look at the entire graph, then A is a cut vertex. Why is that? Because if I remove A, then the number of components in the graph increases from 2 to 3, right? So that there are 3 components now, and therefore A was a cut vertex. I just removed A, of course, it also removed the edges incident to A. Similarly, I can see that B is a cut vertex, C is a cut vertex, and D is also a cut vertex, right? So this disconnects, so therefore C is a cut vertex. Similarly, D is cut vertex. So we have several cut vertex. Now what about the cut edges? E is the only cut edge here. If I remove E, it increases the number of components. And there is no other edge whose removal increases the number of components. Right? Just by removing one edge, you cannot increase the number of. So E is a cut edge, and A, B, C, D are cut vertices of this graph. Now, if you think about the cut edges, you can show the following theorem. Right? An edge of a graph is a cut edge if and only if it does not belong to any cycle in the graph. Okay? Now, can you think of a similar result for cut vertex also? Right? So, can you say something about the cut vertex? Not exactly the same, but think of this. Now, here we are going to prove this theorem that an edge is a cut edge if and only if it does not belong to a cycle in the graph. Now, usually a cut edge is also called a bridge, right? So we also have this notion bridge. So if you see that E is a bridge, then you can take can assume that it is basically an edge whose removal increases the number of components. Now, the deletion of an edge affects only its component, right? So to prove this theorem, you notice that if I have several components in the graph to start with, and if I delete an edge, the number of components in the graph increases only if the component itself increases the number of components, because this edge cannot change the connectivity of any other component, right? So therefore, without loss of generality, we can assume G is connected, because if it increases the number of components, then it must definitely increase the number of components from its part, right? Its own component. So we will start the assumption that our graph is connected. Now, first part to prove one direction is very easy, right? If you take E to be any edge, right? Let's say equal to xy, then G minus E is connected, right? Means that G minus E has an xy path, because by a graph being connected, we say that there is a path between any two vertices. Now G minus xy is connected means that x to y there must be a path. Now xy, if there is a path, take the xy path, and in the graph we have the edge E, right? Now xy, edge E basically connects x to y. So if I have an xy path, then the edge E allows us to go from y to x. Now the definition of a cycle is that you take a path, right, UV path, and then take the edge V to U, right? So that is the definition of a cycle. So therefore, from that you see that the graph must contain a cycle, right? So if removal of an edge keeps the graph connected, then we know that this edge is part of a cycle. Now we have to prove the converse. So to prove the converse, we assume that E is in some cycle of C, right? We have to show that after removing the edge E, the entire graph remains connected. Now for any pair of vertices U and V, we can we have to show that G has some UV path, right? Now, if you start with the graph G, the G is, we are looking at a graph which is connected, because without loss of generality, we can assume that. So therefore, since G is connected, G has a UV path, right? So let us call this path as P. Now, if the edge E that we are going to remove, right, is not part of the path P, then removing this will not change the connectivity of U and V, right? So it will still be connected. U to V will be still connected, right? So there is a path from U to V in G minus E. Right? So U is interconnected to V in G minus E if E is not a part of the path P. Now, suppose E is part of the path P, right? So if E is actually part of the path P, then we can assume that by symmetry. So you have this UV for any arbitrary pair of vertices we are taking, right? So UV, there is a path, and U and V are connected or not in the remaining graph is what we want to check. So in the previous example, we said that if E is not part of the UV path that we are considered, then U and V are not going to be disconnected after removing E, right? Because there is the path P itself is still there. So our assumption is that the edge E is part of the path. And then if I remove, what happens? So if E is part of the path, then the UV path must go through the edge E, right? And then I have a U to X and X to Y edge, and then Y to V path, right? Or it can be U to Y, then Y to X and X to V. But because of symmetry, I can assume one of these, right? So I can say that in the UV path, the edge xy, x appears before y in the path. So now with this assumption, right? So you have this property that u to x there is a path, right? U x interconnection is there, then xy the edge is there, and then y to v the edge is there. So the three interconnection relations by transitivity will give you U to V is connected. But now we have removed the edge XY. So what happens if I remove XY? Now if I remove XY, we said that there was a part, the edge E was a part of a cycle, right? Now because it was part of a cycle, X to Y there must be another path or a walk, right? So there is an XY walk, and together with the XY edge, right, with this path XY path, it was forming a cycle. But now if I remove the edge XY, still X to Y there is this path, right? Because it was part of the cycle. And then we added so now X and Y are interconnected through this path, right, in C, right? So if C is the cycle, then through the remaining edges of C, there is a path connecting X to Y. So X and Y are interconnected, right? So any walk is basically saying that there is also a path, right? So now U to X, there is a reachability, right? So U to X are reachable, then X to Y reachable through the path in C, then Y to V is reachable through the original path B, right? So it's a subpart of the path B. So U to X, the path through the original path, Y to V, the original path is still there. Then X to Y, there is a path through the cycle C that was XY was part. Now the interconnection relation is an equivalence relation. So therefore, because it is transitive, if Ux there is a connection, and Xy there is a connection, and Y to V there is a connection, then by transitivity U to V there is a connection. So therefore, there must be reachability between U to V, and therefore G minus E is also connected. So this is the completion of the proof. Now the graph, a graph G is defined to be K connected if I cannot remove less than K vertices to disconnect the graph. Okay, so I start with the graph G which is connected, let's say, right, and then if I cannot, if I have to remove less than I cannot remove less than K vertices to make the graph disconnected, then the graph is said to be K connected. Now there is so this is what's called K connecting. So I by removing less than K vertices, I cannot disconnect. Then the graph is K connected. Now the connectivity of a the vertex connectivity of a graph is the largest K such that G is K connected, right? So if I if I make kappa plus 1, so if kappa of G is the largest K such that G is K connected. Now if I take kappa plus 1, then there is a subset of vertices whose removal disconnects the graph, right? So therefore the connectivity is the largest K such that G minus K is connected, and here are some examples, right? So if you look at this graph is 2 connected because one can verify that there is no cut vertex in the first part, right? We don't have any cut vertex here. On the other hand, it is 2 connected, and its connectivity 2 because I can find a separating set of size 2, right? For example, this vertex and this vertex. So if I remove these two, then there is no path from, let's say, 1 to 3, right? So therefore the number of components increases. So therefore this is a separating set, and then you get that we have to remove 2 vertices to make the graph disconnected, and with 2 you can actually disconnect it, and therefore connectivity is actually 2. On the other hand, this graph has connectivity 0 because the entire graph is not connected. So even removing 0 vertices, the graph is still disconnected. On the other hand, if I just look at one part of this, right? Let's say I'm just looking at this as a graph. Then this graph has connectivity 1 because it has cut vertices. This is a cut vertex. Removal disconnects the graph, right? Increases the number of components. And the graph by itself is connected. Now, a graph G is L edge connected if G minus F is connected for every F subset of V. Okay. So similar to vertex connectivity, I can talk about edge connectivity. So we say a graph is L edge connected if G minus F is connected for every F in every subset of edges where the cardinality is strictly less than L. Right? By removing less than L, I cannot disconnect the graph. So therefore, it is at least. Edge connectivity is the largest, again, the largest natural number, such that G is L edge connected. Now, here is another set of examples. If you look at this graph, what are the edge connectivities, right? So if you look at the first graph, it is 3 edge connected because without delete, with I cannot remove just 2 edges to make the graph disconnected, right? This part. Right. So now, so therefore, but I can remove just 3 edges. Right, to make it disconnected. So therefore, it's 3 edge connected. On the other hand, the graph on the right side is 2 edge connected because I cannot remove just one edge. There is no bridge, but I have to remove 2 edges. I can remove 2 edges to make the graph disconnected. Right? These two, for example. Right. So therefore, its edge connectivity is 2, and the edge connectivity for the previous graph was 3. Now, what about the edge connectivity of the graph 3 number here, right? What about this? So, if you look at the edge connectivity of this, one can, it's not immediately clear what is it. But if you look through it carefully, you will see that it's actually 2, right? You can find a 2 edges whose removal disconnects the graph. So, what are these 2? So, you should look for it before you continue. So, if I remove these 2 cross edges, then you will see that the graph is actually disconnected, right? This part, there are these 2 parts which are superimposed, and there are no edges connecting. There's a the blue vertices to the other remaining vertices, right? So the graph is 2 connected. Then what about this one? Here the vertex connectivity is actually 1, right? You can verify that vertex connectivity is 1 because it's a cut vertex. But the edge connectivity, for example, is 2 because I can remove these 2 edges to disconnect the graph, right? Either these 2 or these 2, right? Either of these will disconnect the graph. Now, so you can verify this and then look at several examples. I encourage you to look through several examples before continuing further. Then you will observe the following, that for any graph, the vertex connectivity kappa of G is upper bounded by the edge connectivity lambda of G. And then this is upper bounded by the minimum degree of the graph. So this should be kind of intuitively clear, but I want you to give a formal proof. So think about this, why vertex connectivity is less than or equal to edge connectivity, less than or equal to minimum degree. And we will use this result later in the now. Here is another important notion that we want to look at, which is that of bipartite graphs. The graph G is bipartite if I can write the vertex set as a disjoint union of two sets, V1 and V2, let's say, such that both V1 and V2 are independent sets. So if you remember what are independent set, an independent set is a subset of vertices where there are no edges between these vertices, right? So then it's an independent set. So if I can partition the entire graph to two parts, right, two independent sets, and all the edges are basically across, right? So it goes from one of the sets to the other, but these two are independent, so there are no edges. So here is a nice representation, right, of the bipartite graph, right? So I have this part, let's say A, and there is this part B, right? So A and B are independent sets, and A to B, the edges are between A and B, right? So any edge has one of the endpoints in A and the other endpoints in B. So the induced subgraphs on V1 and V2, right, have no edges, then it's a independent set. So an example on the right hand side, right? So the vertices marked in red form an independent set. There are no edges between them, and the remaining vertices form another independent set. Therefore, the graph is bipartite. So you can verify that all the edges are going from the red vertices to the other vertices. Now, a graph this is a very important theorem. A graph is said to be bipartite. I mean, a graph is bipartite if and only if the graph has no odd cycles. Okay, so this theorem I want you to try to think to prove. We will prove it here, but just think about this for some time. And one part is immediate, right? So I can see that if the graph is bipartite, then it cannot have odd cycles. Why is that? Because if the graph is bipartite, let us think of any cycle, right? I start from a vertex, then after going and taking edges, I have to come back to that vertex. Now, since the graph is bipartite, if I take any edge, it actually alternates the sides, right? And therefore, right, since any walk alternates between x and y, to return to the starting vertex, you have to take an even number of edges. And because every closed walk is of odd length, I mean even length, there is no odd cycle, because if the odd cycle itself is an closed odd walk, right? So therefore, this is clear. Now to prove the other side, suppose the graph has no odd cycle. So we want to construct a bipartition for the graph. So we are going to prove graph is bipartite by constructing a bipartition. Now let's take x to be any component of the graph. Okay. So because if the graph is bipartite, then every component is bipartite, right? Because I have a partition into two independent sets. Then look at the components. Each one has a partition into two independent sets. So therefore, I just start with one of the components. So H be any component of G, and take a vertex U in X. Now what I can do is that for the vertex U in H, every UV walk, right? So take the starting vertex U, then fix any other vertex in the component. Then look at every UV walk in the graph, because there, if I take any vertex outside the component, there is no walk at all, right? So I can look at the UV walks from any vertex U to the vertices B. Now, once you fix a vertex B also, right, then you can have several UV walks, right? In the graph, there could be several paths or walks between a pair of vertices. So look at every UV walk. My claim is that every UV walk has the same parity, which means that the length of every UV walk is either all odd or all of the walks are even length. Now, why is this true, right? So our assumption is that we start with a graph which has no odd cycle. Then we take some component. Then I start from some, fix some vertex in this component. Then I look at all the, we walk for every vertex B, right? Every vertex B I take and then find all the UV walk. Now, UV walks for every, once you fix V, every UV walk has the same parity, right? It is all odd length or all even length. Now, why is that? Suppose you have two different UV walk with different parities, right? So U to V, there is an odd walk, and then U to V, there is suppose an even walk, right? Now, so let us say that W1 is a UV walk of even parity and W2 is a UV walk of odd parity. Now, the walks may be intersecting, may not be intersecting, right? We don't care about they are intersecting or not when we are talking about walks, because walk itself can intersect itself. So let us look at all possible UV walks. So I have a walk W1 from U to V. Then there is an odd walk U to V, which is W2. Right. So one is even and one is odd. Similarly, it could be like intersecting, right? U to UW1, right? UV is an even walk. Then W2 is an odd walk. Now, no matter what, I look at the U to V walk and then V to U walk through W2. So I take W1 first, then take W2. So if I go from U to V through W1, then V to U through W2, or in this case, it could be repeating vertices, edges, subpaths, everything, right? Doesn't matter. Whatever it is, I look at this walk from U to U itself. Now this walk is a join of two walks W1 and W2. So the length of this walk is the sum of the length. So it is basically an odd length closed walk. So I get a closed walk of odd length. Now we proved, right, at least as a homework I gave you, to prove that if there is a closed walk of odd length, then it must contain an odd cycle, right? A closed walk of even length does not tell you there is an even cycle, but there is a closed walk of odd length, it tells you there is an odd cycle. So I want you to also come up with an example of a graph with some closed even length walk and show that this walk does not contain a cycle as a subgraph. You can have, of course, cycles, but you have examples without cycles. So that's what I want you to do. And once you have the property that if every closed walk contains a closed walk of odd length contains an odd cycle, you will see that the graph must contain an odd cycle, which is a contradiction, right? So the U to V, V to U closed walk, which is the which is the walk W1 plus the W2 reverse contains an odd cycle, right? So now once you have this, we know that every walk must have the same parity, right? So once you have U and every fixed V, UV walks all must have the same parity. So since all of them have the same parity, now I can say that if UV walk is of even length, I collect such V. UV walk is of odd length, I also collect such V, right? So pick out the vertices which has odd walks from U and pick out the other vertices which has even walks from U. Because the graph is connected, the H component H is connected. Every vertex other than U, right? There is a walk from U. Of course, including U itself. U to every other vertex there is a walk, either of odd length or even length. So collect them together and then form the subgraph as follows, right? So the partition as follows. So V1 of the H is defined as set of all vertices in H such that UV walk has even parity. Then V2 of H is the set of all vertices such that UV walk has odd parity. Claim is that V1 and V2 forms a partition of H into independences. So V1 is independent and V2 is independent. Now why is this? Right? So we have to prove that V1 is independent and V2 is independent. So let us take one of them so that there cannot be an edge between any two vertices. So if X and Y are vertices in this V2, let's say, and XY is, let's say, is an edge, right? Now if XY is an edge, I claim that the graph contains an odd cycle. Now why is that? Because if XY is an edge, U to V, there is some walk, right? Whatever it is, I mean u to x, right? U to x there is a walk which has let's say odd parity. Then u to y there is a walk which has also odd parity, which means that their sum has exactly even number of edges. Now together with the edge xy, you can get u to x, x to y, and y to u is a closed walk of odd length which gives an odd cycle, right? Odd walk and then there's an odd cycle. Similarly, if ux is even, again ux is even, yu is also even, right? Because I collected all the vertices with the same parity to v and v2. Therefore, even plus 1 is again odd. So therefore, I again get a odd cycle. So therefore, we get the fact that v1 of h and v2 h which are independent. Therefore, they are both independent sets, and therefore it's a bipartition. Now, for each component, now I can get a bipartition using this, right? So if there is no odd cycle in each component, I can get a bipartition. Now I have bipartitions of several components. I can put them together, right? If whichever way I want, right? You know, v1 of the first graph, v2 of the second graph, again v1 of the second graph, v1 of the first graph, v2 of the first graph, v1 of the second graph, v2 of the second graph, etc. You have the partition, and that will give you the bipartition of the entire graph. So here are some homework questions. So let G be a connected graph, and P and Q are paths of maximum length in G. Show that P and Q must share a common vertex. Okay. So this is a nice homework. Then, if G is a connected graph and PQR are paths of maximum length, can you show that? Right, there is a vertex common to all the three paths P, Q, and R. Either true or disprove, but I want to emphasize that this is not an easy problem. The second question. So if you don't get an answer, don't worry about it, but try to think of this for something. Okay, it's a very interesting question. If you get an answer, please feel free to let me know. Now the question 3, let W be a closed walk that has no cycle of the graph. Then show that an edge occurs twice in succession in W. Okay. So suppose we have a closed walk which does not contain any cycle of the graph, then some edge must occur twice in succession in W, right? For example, I mean, it will be reversing, right? I go from U to W, then W to U back. This must happen for at least one edge if a closed walk does not contain any cycle. Then the fourth question is that if G is a graph and X is a cut vertex, then show that in the complement of the graph, right? Complement of the graph is the graph obtained by making all the edges as non-edges and all the non-edges as edges. So in this complement of the graph, X is not a cut vertex. Okay. So these 4 questions I want you to think about and try to solve. And with that, let us stop for today.